What's up, what's up, what's up? It's your boy, the network. And today's topic is subsection 3.5b, link state. This is a subsection on the objective 3.5, evaluate route and protocol types. This is a topic in the CCNP route exam, exam code 300-101, version 2.0. Let's take a look at the exam blueprint to see where we came from and where we are headed. This exam blueprint, implementing Cisco IP routing, also known as the CCNP route exam, exam code 300-101. We just wrapped up section 3.5a, distance vector. Right? There's three types of routing protocols: distance vector, link state, and path vector. We did distance vector. Today we're doing link state. After that, we're going to do path vector and finally move on to describing the administrative distance. Remember, this is evaluating routing protocol types. So that means we're doing just theory today. We ain't doing no hands-on, right? So link state, as we discussed, there are three routing protocol types: distance vector, link state, and path vector, right? Distance vector basically uses hop counts to figure out which way to go as far as routing packets or forwarding packets. Link state routing protocols determines the path to go by using an algorithm called the SPF algorithm. We'll go further into that as we move on to the slides, right? And it uses this mathematical computation by figuring out which way to go. Remember last video we was using the United States, right? Three ways to go to, let's say there's three ways to get to from New York to Seattle, right? Instead of using the hop counts, or what we did in that video, instead of using toll booths to figure out which way to go, how many toll booths, the least amount of toll booths, the link state routing protocol will use basically kind of like roads that are closed, or it'll figure out, okay, the weather's bad if we go through the Midwest, so we're not going to go that way. We're going to go through this way. Or it might say, okay, this road is blocked off. There's a detour, so we're going to have to go this way. That's what basically the link state does. It basically uses kind of like not environmental variables, but it uses, it thinks about what's going on basically as far as the state of different roads, right? Or the, I guess, yeah, like the state of being for these different roads, and that'll determine. And then it uses this mathematical computation to figure out which way to go. Let's head over to the slides to get to a more formal definition and information. Y'all know I like to break things down into more simpler. That's why I call this channel the dumbed down channel. But it's the CCNA bruh, or the network bruh. And I just decided I just like to dumb information down, even though it's really complex info. So yeah, let's head over to the slides. Let's take a look at this guy right here. You might not know who he is if you studying network information, or Cisco information, or networking material. Basically, you look at this guy. I guess he looked like a I'm not going to stereotype him, but yeah, he is a his name is EdgarDykstra. And he is basically like a physicist. He is a computer scientist. He was a professor in his later years of life. He basically did a lot of stuff, right? So he came up with this algorithm called the Dijkstra's algorithm, fittingly his name, and it's basically a mathematical computation to figure out the shortest path to get from a source to a destination, right? For this exam, the CCNP exam, we are going to be studying, like I said, routing protocols, right? And the routing protocols that we are going to be discussing right now are OSPF and ISIS. They use this algorithm that this guy invented, basically. He's got all kind of algorithms and mathematical computations that he's invented. But as far as routing protocol goes, it uses the basic theory of Dijkstra's algorithm to figure out the shortest path first. And that's why I got this picture from this guy. So let's talk about, again, link state routing protocols, right? There's three types, right? Link state, path vector, and distance vector. Distance vector uses hops to figure out the shortest way to go. There's also path vector, which we haven't discussed yet. And right now, link state. Link state protocols, sometimes called shortest path first, or distributed database protocols, are built around a well-known algorithm from graph theory. See, this is why we don't really have to discuss too much of it, because this is kind of like algebra. Fortunately, we don't have to know the math behind this algorithm. We just need to know the kind of like the basic theory behind it. Basically, it just finds out the shortest way to get somewhere. Simply put. It just uses this mathematical computation to do it. The routers, the CPU inside the router uses the algorithm to figure out the shortest path, right? It uses EdgarDykstra's shortest path algorithm. Examples of link state protocols, like I mentioned before, are OSPF, Open Shortest Path First, for IP, or Internet Protocol, the ISO's ISIS, DEC's DNA Phase 5, or Novell's NLSP. For this exam, we only really need to know OSPF. There is, a couple mentions, like if you read CCNP material, there will be some mentions of ISIS protocol. When you log into a router, you pulling up the routing, the show. If you do show IP routing, pull up the routing table, you'll see a legend, you'll see information on the in the legend for ISIS. However, it's not widely used as OSPF. In fact, OSPF is probably the most popular routing protocol in the world, other than BGP, but BGP is a external gateway protocol, right? OSPF is internal. So moving right along, as you can see right here, it says it right there. I'm foreshadowing what I'm about to say. When we look at this in this chart right here, we got interior gateway protocols on the left and exterior on the right. EGP, which is not really in use anymore, BGP version 4 and BGP version 4 for IPv6. These are exterior ones. And then we got OSPF. We are going to be studying OSPF version 2. We'll be doing version 3 too as we move along the exam blueprint, and ISIS. But ISIS is not, like I said, it's not widely used as OSPF. That's why for this exam, the CCNP exam, we're going to be focusing on OSPF. We discussed distance vector routing protocols in the last video. So if you want to know more about this information, more about these routing protocols, look at the last video. Again, link state routing protocol uses the Dijkstra's algorithm, also known as the shortest path, or OSPF. That's where the name OSPF came from. It came from the SPF algorithm, which is also known as the Dijkstra's algorithm. I know it has a J in there, it's silent and stuff like that. I believe he's from like the Netherlands or something like that. I can't remember, but he's somewhere in Europe. That's why it's a European name, as you can see. So if we look at this path right here, instead of in the last video we used the United States, we're gonna actually use a topology with routers for this example. We are going to be looking at this topology from the vantage point of router 2 to figure out how to get to, router 2, this local area network. It looks like a T right here, but that's the local area network, to reach the local area network that is beside router 3, right? Router 2, that's router 2's local area network. Router 3, local area network, is right here beside him. It determined the shortest path using this algorithm was going to this way and that way. It could have went this way, that way, and then that way, but obviously that's more hops, right? And it would probably cost more. Let's see. 2 plus 10 is 12, right? Plus that's 22. Plus that is 42. Plus 5, 47. And then plus that's 49, right? So the cost would have been 49 if we went that way. Fortunately, SPF does not use hop counts, right? It uses the SPF algorithm, which in the last video I forgot to mention the algorithm. Distance vector routing protocol is used. That's called the Bellman-Ford's algorithm. I put the notes below just in case you got to open up the notes to really see what the algorithm was. I did not. I failed to mention that. I'm just reiterating that. Just look in the notes in the last video. You'll see more information on that. I even left a couple links. I forgot to mention that. But the algorithm for today we're going to be discussing is the Dijkstra's algorithm, also known as the shortest path first. As you can see, the cost to get from router 2's LAN to router 3's LAN was 27, right? 2 plus 20, that's 22, plus 5, 27. That don't make no sense. Hold on. 22 plus 5, 27. It should be plus 2. I guess it don't count. Oh, it don't count the original local area network. You just starting from the router on. So 20 plus 5, right? That's 25 plus the 2. That gives us 27. Simple math. That's why we don't really. Now, if you really want to, you could Google Dijkstra's algorithm to really know the math. But like I said, we really don't need to know. It took me back to my algebra and statistics course back when I was going to school and stuff. We really don't know the math behind it. We just need to know. This kind of simplifies it by looking at this. Here's another example. The shortest path to a destination is not necessarily the path with the least amount of hops, right? So in this case, it is the least amount of hops and it costs less. So let's say we trying to get, this is the routing table for router 1, right? We're looking at the vantage point of from router 1 to get to router 3's local area network. These are the costs, and that's what it does when it builds a routing table. It comes up with the costs instead of how many hops. Distance vector counts how many hops. Okay, it takes 5 hops to go this way. It takes 10 hops to go this way. It takes 15 hops to go this way. It's going to pick the least amount of hops. So it takes 5 hops to get there. But what if the cost was like 500 to go this way as opposed to say 22? It'll still pick the least amount of hops. That's what's wrong with distance vector routing protocols. SPF don't do that. It defines a cost for each of these links, right? And we're going to get to the reason why they call it link state, right? We discussed that too. Let's bring it back to the map, to the United States. It doesn't want to go this way because there's construction that way. So we're not going to go this way. It doesn't want to go this way because we know if we go take that way from New York to Seattle, the weather is bad. So we don't want to go this way. So that's the state of those links, right? We're going to go this way because the weather is fine. There's no construction. It might be a little longer, but you know what? The weather, we know we can go this way because that way is blocked. So we can't go that way. Link state routing protocols do that. Distance vector don't really do that. It just picks the least amount of hops. And that's another thing with, I'm kind of going off topic here. Static routing goes that way whether there's construction or not, because it's static. It's just going to go that way. And that's what's wrong. You would have to, if you would have to make changes in your routing table or your static routes to actually go somewhere else. That's the beauty of dynamic routing protocols. Link state routing is a type of dynamic routing protocols. OSPF is one of those types. So you want to pause this, freeze frame it to kind of look at it. I'm not going to explain but this is just in simpler terms of the SPF algorithm. The link state routing process. This is how routers use link state routing protocols to reach convergence. We talked about what convergence was in the last video. Convergence is when all routers have all the paths to get somewhere, basically. That's when you consider a network converged, because it has all the ways to get somewhere. Each router learns about its own directly networks. When you first power it on, it knows about the routers that are physically connected to them with a cable, right? We talked about that too in the last video. The link state routing protocols, it goes in these order too. The link state routing routers exchange hello packets to meet other directly connected link state routers, right? So it's going to know about the routers that are directly connected to it, right? But it don't know the routes that the next router knows. And that's where the hello packets come in to form adjacencies. It says hello to the next routers, and then he realizes, oh, you run an OSPF too? Let's be neighbors. Once they become neighbors, they start exchanging routes that are not directly connected to them. That's what hello packets do. We'll go further into it in the configuration once we get into along the blueprint. They exchange routing updates and routes using first by becoming neighbors by saying hello to each other, right? Each router builds its own link state packet, which includes information about neighbors such as neighbor ID, link type, bandwidth, etc. Right? So it's going to be like, okay, he made a neighbor. I'm router 1, right? He makes a neighbor. He says hello, 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 and he realizes, oh, you're router 2? Okay, let's be neighbors. Now me and router 2 are going to be exchanging information, right? Router 2 is going to be like, hey, I know about these routes. And then I'm going to be router 1. Hey, I know about these routes. We start exchanging information. Oh, okay, I can't go this way because the bandwidth is low. Can't go that way because that route is down. We exchange information. That's what routing protocols do. But first they say hello, exchange information. After the LSP is created, the router floods it to all neighbors, who then store the information and then forward it until all routers have the same information. That's when we can consider them converged, right? Once we all have the same amount of information. Once all routers have received the LSPs, the routers then construct a topological map of the network, which is used to determine the best routes to a destination. And then SPF kicks in to figure out, okay, well, each router runs its own, process of OSPF, right, in the neighborhood or in the network, and then figures out, okay, this is the best way to get there. This is the best way to get there. And then we exchange that. I know some routes. This is the best way to get there. This is the best way to get A. This is the best way to get Z. I exchange that with him. And then that's how we become neighbors, and we exchange routes, basically. Link state routing. So let's get to the definition of these terms that I've been saying throughout this video. I guess I should have said this first. Directly connected networks are the ones that are directly connected to them. Obviously, that's self-explanatory. This is directly connected, like say right here. He's router 1. This serial interface, he's directly connected to neighbor over here through with a cable, right? The link, this is an interface on a router. So serial 000 on there would be a link. The link state, this is the information about the state of the links. So let's say we got this link down here, right? That link could be down, could be up, it could have low bandwidth, it could be whatever its condition is, that is the link state. Now that's why we call it link state routing, because we use the condition of these roads to figure out which way to go, the best way to go. Distance vector don't do that. What does it do? It determines the best way to go by counting the least amount of hops. Also in the last video, I kept saying RIP, the maximum amount of hops was 16. It's not, it's 15. 15 is the maximum amount of hops. And if it goes past 15 hops, it'll be like, it'll consider that route unreachable. 16 would be over 15. And then from that point on, it would be considered unreachable. So it's 15 is the maximum. 16 on, it definitely is not going to add it to its routing table. I forgot to say that. Please look at these notes that I put in below, because I go back and watch these and be like, that's wrong, that's wrong. I guess I just be saying whatever, and then I finally catch myself. Okay, so link state routing, sending hello packets to neighbors. Again, I'm router 1, this is my neighbor, router 2. But he's not my neighbor yet, but I'm going to keep saying hello. I send hello messages. OSPF, for example, sends hello messages, I believe it's every 10 seconds, right? Yeah, every 10 seconds. And then I say hello every 10 seconds. Once I power on, if I'm running OSPF, I wait 10 seconds. Or actually, it sends a hello packet. And then once I realize I have a neighbor, or a potential neighbor, he's going to send a hello packet back to me. Then we realize, okay, we're both running OSPF. Then we become neighbors. It does that every 10 seconds just to see. And then it keeps doing that just to see if he's still alive. The dead timer, I believe, by default is 3 times that or 4 times that. So it's 40 is the dead timer. But we'll get further into that once we discuss OSPF. I'm going off topic here. Link state routing protocols use a hello packet or protocol. The purpose of a hello is to discover its neighbors that use the same link state routing protocol on its link. As you can see right here, router 3, let's do router 1 and router 2, just like I've been saying. They send hello packets to each other. Once they realize they run in the same protocol, oh, we both run OSPF, let's become neighbors. Each router is responsible for saying hello to its directly connected networks. So he is not going to say hello. So router 5 is not going to say hello to router 3 because they're not directly connected. He's going to learn about router 3's stuff through him, who learned it through him, who learned it through him, etc. And that's how router 5 is going to get information from router 3. They're not going to be neighbors, but he's going to receive routes through him, if they're all running OSPF. Link state routing protocol, sending hello packets to neighbors, connected interface that are using the same link. We've mentioned this. I believe this is kind of redundant. Once router learns it has neighbors, they form an adjacency. 2 adjacent neighbors will exchange hello packets. These packets will serve as a keep alive function, just to make sure they are still neighbors. Like let's say router 1 and router 2, right? Let's say they are neighbors, right? They just gonna keep saying hello by default every 10 seconds, right? And then if let's say router 2 dies, I'm kind of going off topic here. Let's say router 2 dies, and he's just gonna keep sending hello every 10 seconds. Let's say he dies at the 9th second, and I send a message. I haven't heard from him in 10 seconds. I'm gonna keep going, keep sending. Actually, I'll wait till 20 seconds. Boom, send a hello message. If I haven't heard from him then, I'll keep going. It's 4 times, I believe. It's 4 times. And then after 40 seconds, I would consider him dead and take him off my routing table. Again, these serve as a keep alive function, meaning I just want to make sure he's still there. Link state routing, the process. Each router learns about its own directly connected networks. This is being redundant here. You want to pause it, freeze frame it, whatever. Contents of the LSP includes information about its neighbors, such as neighbor ID, link type, and bandwidth. They just do this just to make sure we know who is on the network. Flooding LSPs to neighbors. Once LSPs are created, they are forwarded out to neighbors. After receiving the LSP, neighbor continues to forward it throughout the routing area. So router 1 receives information. He has a routing table. He learns about his own network. That's the fourth step right there. Each router floods the LSP. So I know about router 3 and 4, right? Because and 5 and 2, right? Those are directly connected to me as I'm router 1. So I send information to them, right? I know about them, but they already know about these networks, right? So that's going to be redundant to them. I know about 10.1 network. They are not directly connected to them. So I send information about 10.1 to them, and that's how they learn about it. They store it in their database. That's called the link state database. The link state of this network will be kept in their database again. LSPs are sent out under the following conditions. Initial router startup or routing process. So once we power it on, we learn about the LSP. When there is a change in topology. So let's say, for example, I'm router 1, right? And let's say the local area network over here goes down. I let them know about it. Then they can be like, okay, we can't really go through that way to get to the local area network on router 1. Then they'll have information that router is down. You don't have to wait every 10 seconds. You don't have to wait every 30 seconds like RIP. As soon as a link goes down, that's why it's called link state. As soon as the link state changes, if it goes down, if there's a change in the route, they will automatically give that update to everybody else. That's when there's a change in topology. That's why it's called link state. Constructing the link state database. Routers use a database to construct a topology of the map of the network. That's the fifth step right here. Each router uses the database to construct a complete map of the topology that computes the best path to each destination network. So everybody has their own link state database, and they figure out, okay, router 5 has the best way to get to there, etc. That's basically what that says. And then that's their link state database. LSPs from router 2. I'm not going to explain all this. If y'all want to look at all this, go ahead and pause it, freeze frame it. All right, we back. Again, this is an example for router 1. That's his basically his routing table. These are the costs to get everywhere. And everybody has their own just like this. So router 3 has his own version of that. Router 2 has his own version of that, etc. And then there's their states for each one. Let's pick one. Router 1's link state database from router 2, right? So this is his database. He's connected to neighbor 1 on network 10.2. Which is, that's not going to be good enough to explain because we don't have the IPs on here. Okay, so link state routing, the shortest path tree, shortest path first tree, SPF tree. Again, that's the term that's used by the algorithm. Now we can explain it because we have IP addressing here. Building a portion of the SPF tree. The process begins by examining R2's LSP information. R1 ignores the first LSP reason because he already knows he's connected to router 2. So let's say right here, router 1, router 2, the LSP from router 2, right? The LSP from router 2, he already knows about this information connected to router 1 through the 10.2 network. He already knows that. He has a connection to the neighbor router 5. This he did not know, right? Because he's not directly connected to him from router 1, right? And then he has information that he has a network 10.5.0 with a cost of 2. So the local area network that is over here is a cost of 2. Router 1 did not know about that. Now he knows about it. That's building a portion of the SFP tree. Router 1 uses the second LSP, which is this one right here, connected to router 5. Reason, router 1 can create a link from router 2 to router 5. This information is added to router 1's SFP tree. So this information he did not know about yet, right? This right here. The network 10.5, he did not know about it, so he's going to add it to his link state database, or basically his routing table. And then same thing here. He uses the third LSP. He adds that one, which is, I believe, right here. Yeah, so he used that one the first time, 10.9.0 network, which was this one. He learned about this one. That's the second one, I'm sorry. So this is the second LSP that he learned about. And then the next one, he learned about the local area network, which is right here, the 10.5.0 network. And again, this is pretty much redundant. Determining the shortest path to determine destination determined by adding the costs and finding the lowest costs. So so he adds costs to them, and then he determines the lowest cost. That's where SPF kicks in. We don't need to know the math behind it. We just need to know the theory behind it. The CPU on the router does the calculations. If you really want to get into that, that's beyond the scope of this exam. You can take a statistics course or some sort of algebra or calculus or something like that, a college course, to really know the math behind it. For the CCNP route exam, we just need to know that the CPU uses shortest path first algorithm to figure out the shortest path. Once the SPF algorithm has determined the shortest path routes, these routes are placed in the routing table. Simply put, it comes up with the costs and the shortest path. It tells you which ones are directly connected, right? The cables, really. And then the remote networks that are not directly connected to them. So, for example, from router 1, right? The 10.7 network is not directly connected to him. Where's 10.7? Right here, right? He's not directly connected to him. But he learned about it through router 3 on serial 001. The cost is 15. 10 plus 5. Right? That's just one example. You can pause it, freeze frame it, whatever. It's best to do this hands-on. Remember, this is we just discussing the theory in this, but once you play with the router, we'll do that as we get along these videos. But that's how you learn this stuff. Lab every day, hands-on. Here's the advantages of link state routing protocols. So right here we haven't added path vector is the third type in here. We should have had path vector added on here to see the pros and cons. But as you can see, distance vector does not build a topological map. Link state does. The router can independently determine the shortest path. So each router runs the SPF algorithm in its CPU, right? They do it independently. They don't just have the same exact information. Distance vector don't do that. Link state does. Convergence is faster. Distance vector is slow. Periodic event-driven routing updates, generally no. Link state, generally yes. So yes, distance vector does react to, let's say, bad weather if we go this way, but it does that periodically. Link state does it as soon as it happens. As soon as he knows, it's just like Google weather. As soon as he knows there's bad weather, he's not going to go that way. He's going to take the other way. Or as soon as he knows that this road has construction, he's going to go the other way. Distance vector waits at a periodic, like at an interval. RIP, routing information protocol, does it every 30 seconds. He won't check this road. He won't check the way to go this way until like 30 seconds. Then he realizes, oh, we can't go that way. It's construction that way. Then he reacts, let's go this way. But he'll still pick the one that has the shortest hop, which is not always the best case. So the requirements for a link state routing protocol, it uses memory, right? It uses more CPU power, and the bandwidth requirements, the initial startup of link state router can consume lots of bandwidth, right? So that's why you want to pick the router with the best CPU or the fastest CPU, because it does a lot of mathematical computations. That's what a CPU does, right? It's a central processing unit. It does all of these mathematical computations to figure out the best way. It could take a lot of processing power on your router if you were running these routing protocols. However, it'll figure out the best way for you. Two links that this is all redundant. We've talked about this. There's two versions of OSPF really. Version 2, which is for IPv4, and version 6, which is for IPv6. ISIS, again, it says discussed in CCNP. If you pull up right now, this is why you need to make sure you are studying the correct up-to-date material. This is a prime example. It says here, discussed in CCNP. I got this PowerPoint slides from, I just kind of modified it myself. I should have edited that part out. You might have glimpses or mentions of ISIS, but we don't really need to discuss ISIS fully on the CCNP route exam. You can pull up the exam blueprint right now. I'll even put a link in the description below on how to get to. It is not discussed in CCNP. It is briefly mentioned. So that's why you need to make sure you are studying for the up-to-date material. Make sure I just happen to know this because I'm studying for it. Oh, here's a summary. We're just going to race through this real quick so we can keep it under our limit. Link state router protocols are known as SPF. It's summarizing the link state process. First, they learn about the directly connected networks. They say hello to figure out their neighbors. Then builds the link state packets, figure out, okay, this is the bandwidth, here's the weather if you go that way, here's the link state of that. If you go this way, the link is down. Then he builds that packet. Then he floods that information to his neighbors. And then the neighbors use that and add it to its own database. That's called the link state database. And we'll discuss more of OSPF once we get to it. We're just discussing link state types and defining what they are. And then it calculates the best path to each destination. A link, again, is a interface on a router. The link state is basically the state for, okay, the bad weather this way, this link is down. I always say use weather and roads, again, because that's what I do. When we talk about networkings, we like to compare them to roads and highways on the actual road. Figure out the subnet mask, type of network, cost associated with link, neighboring routers, etc. And that's pretty much it. If you like this video, please comment, like, subscribe to the network.